Anastasia Shuba, and I'll be presenting to you AntMonitor, a related project to Lumen. This is joint work with my advisor, Athena Morkapoulou, and some members of our lab, as well as actually some other DTL grantees, mainly David Chofnes and Zubair Shafik. So I thought I would have, there we go. I thought I'd have 15 minutes, but now I have, I don't know, 5. So I'll skip a lot of motivation. You guys already know there's PII leakage. It's bad. The apps send it to third-party servers. There's been a lot of related work, some of it rooting the OS and making rooting the operating system or making custom operating systems. These methods are not valid for mass-scale adoption, so there's been VPN approaches like Recon by another DTL project, and our own AntMonitor, as well as Lumen. So I'll briefly review the system that we presented last year. This is our application that we made available a few months after receiving the grant. So the idea here is we intercept all the network traffic, then we can do some online analysis, such as detecting privacy leaks and maybe ad blocking. And you can imagine your own applications there as well. We also do offline analysis by putting the packets on the queue, and any computationally expensive operations you can perform there offline. For us, it was data collection. For you, it could be something else. So we thought this is better. Instead of delivering it as an app, we thought we'd package it as SDK that other developers can make use of. So we provide all these functionalities in our library. So you can get access to the packets, as well as get access to any TLS packets that we decrypted with SSL bumping. You can also access the offline analysis module. We provide capability to map each packet to applications that generated them. And we also have a DPI module available for you. That's very fast acrostic search to search for any strings that you may be interested in. So this SDK is now available online. That was the main goal of the project when we received the DTL grant. We do ask you to email us for login credentials, because we protect it for now. And we've spent a lot of time testing it with different partners. It's pretty stable, but I'm sure there's a lot more bugs we can fix with your help. And just briefly mention, we did do a lot of optimizations to make this work fast. As Narcea mentioned already, it's pretty difficult to achieve these good performances. We started out with just 0.8 then megabytes per second, which is obviously awful. Then we went up to 25 and then 80. And our acrostic search is also just 1 millisecond per packet, so you guys can make use of that without reinventing the wheel. So what happened since then? We've built several applications on top of our SDK, just as demos. You can build your own, too. The first one is for privacy leaks. We call this one Ant Shield, and the other one is for ad blocking. We call that one Ant Wall. So for privacy leaks, obviously, we're looking at the outgoing traffic. And again, there's been related work. For us, we don't need the VPN server in the middle. We keep the VPN locally on the device. So some of this we presented last year. We were able to detect any strings that are readily available on the device through Android APIs, such as advertiser ID, your phone number, email. All of these things are available to all apps, including our own. So there's some obvious limitations to this. The user might not want to share any other PII with us. Like, we allowed them to enter other information, but they're obviously not going to share the password with us. So we decided to look at another related DTL project that was Recon. They had an implementation on the VPN server here, so they were not on the device like us, but they were able to detect strings that were not known a priori with some machine learning classifiers. So we set out and to see if we can achieve both, find unknown leaks, and also have that running on the device. So I will briefly review the Recon project by David Chofnes' group. They made it available, and we had nice interaction with them, thanks to DTL. So the idea here was, given a packet, you feed it to a classifier, and it tells you if there's a leak or not. Packets look like this. There's some URL, some headers. In this one, we can obviously see there's an advertiser leak, and there's a corresponding HTTP header to it. So what Recon did is they extracted words from these packets. They eliminated any words that appear frequently in a lot of packets, as well as the PII values themselves. They repeated this procedure for multiple packets. So they ended up with a huge vector of features. They fed them to a classifier. They found that the decision tree performed best. So if you do this on all the data in their data set or our data set, you usually get 233 nodes, excluding the leaf nodes. This is a very giant tree, takes hours to train, and has accuracy of only about 80%. So they improved this by building per domain classifiers. for each domain, there's a separate classifier. These ones, 95% of them had higher accuracy than the general one, took only minutes to train, and they came out to be really small and intuitive trees, such as this one. So after the classifier, you still need to know what type of PII it is. The classifier only tells you if there's a leak or not. And then we need to figure out what type of leak it is. Recon built an interesting heuristic to extract this based on HTTP key value pairs. So we thought this was a really cool project. We got their code thanks to DTL. They made it available, and we decided to see if we can implement this on the device. In the beginning, we were actually not sure if this is possible. Machine learning is pretty expensive. Their system was running on the server. We wanted to make it on the device. When we put it, just their code, we put it on the device. The parsing time to extract the words took 36 milliseconds, which is not super good for a device. It leads often to TCP timeouts, so the pages were not loading when we just used off-the-shelf Recon. For them, it was OK, because it was on a giant server, and those, they're a lot faster than a small device. So we thought long and hard about how to fix this, and then how to avoid extracting all these words. And we realized we can just look at the trees themselves. We don't need all the words in the packets. We just need to see what exactly appears in the tree. We already have a way to search for strings we know in advance. So we extract all the features that appear in the tree, and then search for them with our ahocratic algorithm. And then another parsing time here was to extract the PII type itself. Right here, we wanted to avoid that as well. So for that, we went towards multi-label classification, and we built a separate tree for each PII type. So when you go through our classifiers, it immediately tells you what type it is, not just if there's a leak or not. With that, we not only were able to achieve this in real time, but we also improved the accuracy from 72 to 99% in distinguishing the PII type. And the overall accuracy, meaning distinguishing between no leak and the PII type, went up from 89 to 99%. So here's a summary of our results. As I've already mentioned, we improved about 20% over Recon. Instead of building per domain classifiers, we also did per app, just for some performance benefits. Because I'm out of time, I will skip some of these details here. But basically, this is a system architecture. We build on top of our own library. Then we use DPI to extract the features, feed them to classifier, and then make a decision based on if there's a leak detected or not. Again, there's a lot of other performance improvements. I'll skip those over for lack of time. And we were going to use this in the future for some distributed learning. Basically, now that we have this running on the device, each user can have his own data, and we wanted to see if the user should share that data, if that brings any benefit to the classification or not. So that wraps up the privacy leaks. And now I'll go into our second project. So as we know, the applications request ads from their servers, and then the ad gets fetched from the server and gets displayed on the device. So this already fits into our system. That's why it won't take too long. So the very similar architecture as before. We collected a little bit of data using EasyList AdBlock Plus, as well as some manual labeling. We wanted to create an effective and efficient cross-app ad blocker. And we use this with machine learning. I know there's been previous approaches to detect ads with machine learning, but most of them were per flow. And we wanted to do it per packet, so we avoid keeping states for each flow. So yeah, here's some preliminary results. Basically, we compared against EasyList, which achieved 77% accuracy and F-measure, sorry. And our main finding was that actually looking at the PIIs kind of says it all. So just with these two features, device ID and advertiser ID, that gave us 98% F-measure on our small data set. And then regardless of how many features we used here, we went through many different feature sets. We have availability for real-time prediction in the order of milliseconds. Here's a comparison to EasyList. And EasyList, just for your knowledge, works on URL and headers. And with that alone, we're also able to achieve a pretty high F-measure here. We tested this in the wild, basically testing on applications that were not part of our original training data set. And we, again, had low false positive, low false negative rates here. Computed low CPU usage of our app and small memory usage here. So just to conclude, today I presented to you our SDK that's now available on this link. And I presented to you two applications. The first one was AntShield for detecting and preventing privacy leaks with DPI and machine learning. And the third one was AntWall for using machine learning to detect and prevent ads. And that's it.
Fantastic. Thank you very much, Anastasia. Thank you very much.